Big Mac here. So today we have another QualQuest question. This is definitely from our numerical ordinary differential equations part. We're given a basic differential equation, y prime equals lambda to the y, or times lambda y. And we're given this specific updated scheme. So we have our known value yn, and we want to try and find yn plus 1. Right here is typically, this is similar to the form of a trapezoidal method. And then we have this extra term down here, which includes the second derivatives of both the point that we already know and the point that we don't know. So how are we supposed to figure out, it's weird because we need to try and figure out what our derivative is at the point without actually knowing what our point is yet. But given this scheme, we are asked to determine the order of accuracy. And what that means is for a step size h, if we have h or increase it or, take 1/10 of it, how much more accuracy can we expect out of our end solution? That's what that means. Hopefully, we're experiencing some technical eraser difficulties, but hopefully you guys can see this. And again, put it in full screen if that would help. But basically, in order to determine the order of our operator, we need to compare to this ratio, yn plus 1 minus yn over our step size h. So obviously that's meant to mimic our derivative function y prime. A couple things that we can use for this particular problem is that since we know that our derivative is just lambda times our function y, then we can just substitute that into our derivatives here. So, for example, yn prime is just lambda times yn, and yn double prime is lambda squared times yn, since we're basically taking the derivative of this part again. Thus, writing our numerical scheme into our differential operator, we have our rough approximation for y prime on the left side. I divided everything through by h. So now we have these terms left over, and I plugged in our derivatives values earlier. So of course now we have everything in terms of yn plus 1 and yn. So the best way to deal that is to rewrite yn plus 1 in terms of yn using a basic Taylor series. Now the question is, how many terms do we want to expand this out to? Again, we're looking for the highest order of accuracy possible. So if we stop too short, we might underestimate our answer. So this is where some nasty algebra is going to come in. And so using a basic Taylor series expansion, where remember y sub n plus 1 is basically our exponent, or our extrapolation of our point y of n, a certain distance h apart. So using our traditional Taylor series expansion, so we have y of n plus the distance between the 2 points, which is h, times yn prime plus h squared over 2 yn double prime, etc., etc. You keep having your h to a power over that power factorial times yn to that derivative. But of course, since we have our nice y prime is lambda y equation, we know that any yn to whatever derivatives is just lambda, lambda to that power times our original point. So we rewrite it as here, yn plus lambda h yn plus h squared lambda squared over 2yn, etc., etc. I'm carrying it out to this term up here, the fifth power, h to the fifth lambda to the fifth yn over 120, which is 5 factorial. So on the left side, here's our difference quotient again, and we're going to have everything in terms of yn times these 5 terms. And of course there are more, but this is as far as I'm writing it out. So now working on the right-hand side of our equation, where we had the bulk of our numerical scheme, we now implement yn plus 1. We introduce our Taylor series for that. So basically, again, this is just a lot of nasty algebra. Not so much in combining terms, but just the number of terms that we have to keep track of. So go ahead and pause if you need to look at it for a little longer, but I'm going to the next screen. Okay, so going through this final step of computation, I noticed that I actually had a minus sign flipped around. I will fix that in annotations. Unfortunately, that hasn't affected anything up till now. But so what we're going to do now is, we rearranged all our terms. I tried to organize these as well as possible to fit on the screen, but these ones up here are from our 1/2 terms, and then these ones here are from our h over 12 terms. You'll notice that actually we had a term cancel out. Our lambda squared terms canceled out since we had lambda squared on lambda squared yn minus lambda squared yn. So that term disappeared. And I rearranged terms a little bit here, down here. So we have lambda yn plus h lambda squared over 2yn plus 1/6 h squared lambda cubed plus 1/24 h cubed lambda to the 4th plus a couple more terms. So now, in order to determine our accuracy, we have to compare our left and right hand sums and see how much cancels out. So now when comparing our left hand terms and our right hand terms, we see that most everything matches up here. We've got lambda yn on both sides, lambda squared over 2h on the next part, lambda cubed over 6, lambda cubed h squared over 6, lambda to the 4th over 24th h cubed, lambda to the 4th over 24 h cubed, 1 over 120, 1 over 144. So we have to go up to the h to the 4th power in order to have a discrepancy between the left hand and our right hand notation, or our formulae. So what this means is that for a given step size h, we should expect our error to then be on the order of h to the 4th. So this means that if we were to make our step size 10 times smaller, we would expect about 10,000 times the accuracy. So for solving this kind of equation, this numerical scheme is actually really useful. So that way, if we want to have a good reasonable guess, we don't have to take an incredibly small amount of our step size. We can take a slightly larger one because we know that we're going to have order to the 4th accuracy. Alright, this is Big Mac saying later.